Okay, good morning, student. It's about 9 p.m. For today. I will start to recommend you to go to the Facebook group. Inside the Facebook group, there are a number of examples that have been launched in many years. And for example, for incoming midterm examination, it's supposed to follow these their examples. There's going to be a number of them. Then you got to select the popular one and try to solve it by yourself. Okay, that's going to be the result for you guys for preparing your midterm examination. For today, let me move to chapter 4. We're going to have the problem number 3 for the shear force diagram and bending moment diagram of the beam. And then we will have problem number 4 for the midterm examination on frame. And frame is going to be the column connected with the beam. So that's going to be the frame. I may say this maybe the one for you, but actually it is static also. The level beam. So first you may have the beam model and the frame model. This is your duty. First, draw the free body diagram, and then we will use equation of equilibrium to be what? To the reaction and then the internal forces and internal bending moments. This will be what you have studied in the static. Then use the reaction to draw the shear force diagram, bending moment diagram, and we will focus on graphical method. If you like to draw the shear force diagram first, we have dV by dx equal to minus W, slope of the shear force diagram equal to negative of this the force. Then this equation can be rewritten to be differential of shear force equal to minus distributed force dx, and then use mathematics to do the integration from A to B. Example, this one also from A to B. Then this is going to be V sub B minus V sub A. Or you may call it the difference of the shear force is going to be equal to negative of the area under W between A and B. The area between of the area. Then coming to the third one, if you have upward force, upward reaction, the shape of V is going to be positive. If you have downward force, the shape of V is going to be negative. Okay, that should be mentioned in this pattern. And then you also have the relationship for the bending moments diagram. First, you have df by dx equal to V. The slope of moment diagram equal to shear. That means when you draw the bending moment diagram, you take a look at the shear diagram. When you draw the shear force diagram, take a look at the problem, the model. And then for the second one, do the same thing. You have df equal to V dx, and then you do the integration from A to B. Integration from A to B. You will have M sub B minus M sub A equal to positive of the area integration. Area what? Area. The area of shear diagram between A, Q, B. And then the last one is going to be if you have clockwise movement, delta F is going to be positive. If you have counterclockwise movement, the shape of the movement is going to be negative. Okay. You got to use all of this in many times until you finish the statistical analysis. Okay. But you also try to write the equation for the shear force that, sorry, the equation for the movements that for some time, such as in the last chapter when we determine the reflection based on the method of virtual work. Now, going to the homework, okay, in the homework, the problem is going to be a bit more complicated than you have in the engineering standard, okay. Then the method, we used to use the method of section to draw the shear force diagram and bending moment diagram is not good because, for example, for this one, you got to cut the beam 1, 2, 3, 4 times. You got to use the method of section 4 times to write the shear function, to write the moment function and product graph. So this type of method is not good. So we move to method of graphical method. Okay, and then we also should be able to know the shear force that and the movement that can of the foundation also. The foundation begins in some kind of beam if the foundation is a strict foundation. And then the force of the column will transfer the foundation due to the rigidity of soil. Then the soil may resist the F force in the form of uniformly distributable. That's supposed to be very compact soil. And then you should be able to analyze the foundation, the shear force that and bending moment that. And then we move to the frame. We have some frame, and then we will provide extra example for you at the end of this lecture. Next time when we come, we will have the frame. And all the homework, you must compare the result with the result from substandard program, and result must be the same or almost nearly the same. Okay, maybe different by 1 of calculation. And now we move to many examples. We have reduced wind and frame in various constructions, such as this one. We studied about this week. We should know about 3 years ago. We has reinforced concrete with he got a project from his dad was existing Japanese company building a factory just in Ayutthaya, and then he worked with him, and then he take the project, and then he took the master degree and study about this thing. Okay, this thing is a kind of 4-point loading beams. Okay, and then you have to be able to design experiment. Before you can design an experiment, you have to be able to the shear force that can and bending moment that can in the function. The load going to be P, okay, the length going to be L. All of this analysis going to be in the form of various variables in order to do the experimental design that mentioned about this one on Tuesday in the method testing. Now, for the other one, the P task B may be B task is tested concrete girder. This one is used in the highway bridge. Okay. During the construction of the foundation of the high under the foundation, this beam manufactured in the factory. At the same time, you also build the pier, okay, and later you build what's so called the cross beam. This one may called cross beam, and then this is the pier. You know about it. This is the pier. P-I-E-R. And then foundation, and then you just lift the task is tested concrete further by the crane and put it in the position, and later you just pass the slab. You have a beautiful bridge. Then this is steel. You also have the steel beam. Okay, during the construction, this type of prefabricated steel beam will just lift up by the crane and then connected to the frame of the structure over here. And you may note over here there are stick fender that we also have this one in our steel frame in our F4 lab in order to strengthen the column to resist the force. Okay, this is a type of, if you remember this form, this is a type of can-fit rivet beam. But doing after you install it, that is not enough. Okay, this is from the chapter. You got to be putting the type. Okay, you know the type, right? Putting over here. When you put the type over here, this will change from statically determinate to be statically indeterminate. But you may be able to analyze this kind of composite structure or composite beam in the last chapter of this game. That's all the real thing. Then you, as the engineer, you have a function. Engineer has a function. A function of what? A function to specify. To specify what? To specify the spot of the structure. We call that from previous lecture. Again, teach you how to determine the determinacy and stability. And then the other one, degree of community can be shaped with the shape of support, right? And that is the routine. When we shape the support, we got to provide the detail of the construction of it. If you may notice on this one, you see there is a gap on the top of the front of the small beam and the big beam. This gap allows the small beam to rotate. Okay, this one you may assume this one to be the beam support. Okay, and then for another one, if you will, the bottom of this beam into the column, then this is not beam, we will check to be the fixed support. Okay, so please provide the detail for the construction in accordance with your model. And then this is one of the failure that should not occur. Okay, this is the water tank on the top and put it on the frame. And this frame like of what? The same thing as the example when it last slide of last lecture, the column of the parking garage. This column is to do what? Let all the basic And I don't know, you guys have more to the support center or not. Okay, that is the example in the sickness of you. And if you prevent it, you may put the basic for like this one. But you have to put it in vertical first before you put the basic. And you should put the basic in four direction. Okay, in order to stand increase stability to this way. And number three, I would like you to concentrate on your tributary, okay, or your distribution, the second, your distribution. See, you see, from graphical engineer. Okay, you see, that is the slab. The force from the slab should transfer one way to the beam. Okay, and the beam is quite complex. The beam that is between large column and the column that's not the big beam. The big beam is the beam that connects column to the column. The beam that connects beam to the beam, or the beam between the other, we call small beam. Okay, the load will transfer from small beam to the big beam to the column. That's why I said big beam we call other. That's why we call other. That's before it's connect column to column. We call other. But the one that just connect the beam to the beam, such as this one. Okay, you will call the beam. Okay. Now, for this one also, I would like you to be creative. On the roof is supposed to have day and light load. Okay, light load on the roof is what in Thailand is going to be at least 50 kilogram per square meter. Do what? Work on the roof. If you have roof, okay, or even to clean the roof. And then for the head load of the roof, it's going to be what? It's going to be the weight of the metal sheet. Okay, it's going to be only 10 kilogram per square meter. Then the load going to distribute all over the area. If you are more concentrated, you may put the window. Okay, magnetic plant. Okay, it will work. So this is low-rise building. The window can be 50 kilogram per square meter. Then you every square meter on the roof should be able to take care of 110 kilogram. So we have a party over there. Some things that are our roof to be burdened. Because we transfer the load of the roof to the beam. Okay, the beam. And then there may be many types of beam. Can be the beam cross in this direction and it has the beam in this direction. You got to think the way the force transfer from the beam, from the roof to the beam. Okay, the big beam is going to be transferred from the roof to the small beam. And then from the small beam, in this case, the beam. Okay, to the large beam. Large beam is supposed to be the beam that connects the column. That's the bigger concept. Then you may determine the reaction and transfer the load acting on the structure. And then you may detail the structure and then you model each object and then you analyze it and decide it. And this is an answer. I have, okay, very simple. I have one story. The load transfer from the loop high, okay, to what? To the hurling, okay, and then from the hurling to the results, okay, from the hurling to the pink blaster. If you would like to analyze the pink blaster, the pink blaster is subjected to the reaction transfer from the fluid and act on the laster, right? And then for the laster, is made to have the weight object, okay? And then you make body object, and then you use the to start the analyzing what all the equality, and this one gonna be shear force that bending moment that and this one gonna be the elastic curve, and then you use maximum shear force. This is gonna be what maximum shear force gonna be this one, and you also gonna use the maximum suppose we bending moment because to take this point about this point to take the impact, and then you decide based on impact. You get the section, then you check for the shear, you check for the reflection. That's going to be the whole process. Anyway, we are at chapter 4, and then Ajahn should mention in engineering habit, we starting with given, as you said, this one is given external applied. Applied to what? Applied to the structure. And then the structure should have shear force and fractional stress distributed all over it. This is fractional stress. This is shear stress. Okay. And then the result of that may cause the internal shear force and internal bending moment. But in reality, do we follow the step here? No. In reality, in our calculation, we start from here and then we determine it by free body that and then use equation of equilibrium. This is in what? This is in engineering statistics. Okay. Then later you study the subject of metrics of material. Then you'll be able to begin fractional stress sigma equal to Fy/OI. The shear stress how equal to VQ over IT. Okay. During the process of this one, the body that we use first of all the method of section. And this method of section is different from the past. Okay. But the concept is the same. Each cut has 3 unknowns. That's going to be normal force. Okay. For this one, axial force. Okay, it's going to be perpendicular to the cut section. And then the shear force. The shear force is going to be in parallel to the section. And then we have the bending moment over here. Bending moment is equal to period rotation. Okay. And normal force gonna period linear. And then as you said, for somehow movement, okay, there's a movement. And then for shear is going to be very linear, vertical movement. Each going to have its own function. In our subject, we got to define the sine convention, and as we have the x, y notation, so our x will measure from the left to the right. That's going to be x. Okay. Then if you cut at x, okay, following normal force, shear force, and bending moment specified here gonna be positive. Okay. Anything opposite is gonna be negative. In another free body that has less been cut on the opposite side, you got to follow the third law of Newton. So the shear force over here, positive. Axial force, normal force, we are also positive. And bending moment here is positive. And then if you take part of this one, and then you put the moment on the left and on the right, you will see this kind of moment will provide positive moment. Under positive moment, you got to reinforce this beam by the steel on the tension side. Okay, you get it like this one. That's the new concept. When it's subject that you negative moment, you got to put more steel on the top surface. Okay. Now, coming to the procedure, again, we start with the same thing. We body diagram, and then we use the equation of equilibrium that Ajahn has mentioned to determine the reaction. That's going to be the whole free body diagram of the beam. Okay, you have this one. You can determine by what? Summation of the moment at A first equal to 0 to eliminate A sub x and A sub y. Then this one you will get B sub y. Then you have summation x sub x equal to 0, you got A sub x. You have summation of x sub y equal to 0, you got A sub y. Okay, Ajahn helping you try to put this one 1 meter, 1 meter, 1 meter. It is going to be 10 kilonewton. It is going to be 20 kilonewton. It is going to be 60 meters. Okay, can you define it? Because the block is that. That's specify the load and the dimension. And then you will cut any section. Okay, when you cut it, you got to specify the side, the shear, the normal force, the moment, follow our sine convention. Okay, and then you got to use the equation of equilibrium again to determine it. If you say this is 1.5 meter, and you determine the internal forces and also V. Okay, and then you need to be M, you have to be right, follow what the classical defined. And then in engine static, we do what? Engine static, we will specify it only at the 1.5 or number, and then we specify it to be X. And then said, if we specify it to be X, we will start from the left to the right. Now, you are not only dealing with N, V, and M. Now, N is going to be as a function of X. V is going to be function of X. M is going to be function of X. Before that, if we say this is 1.5 meter, this is going to be only value. Okay. But later, when we change to N, this is going to be the function. The function will be used to draw the shear force diagram, moment diagram. And also, we need to mention much about what's so-called normal force diagram. Most of the time, we draw normal force diagram for the frame building, or at that one way for this one, axial force diagram. This is important for the problem. Let me move you to this one, and I assign you to start thinking by yourself to determine the internal force and bending moment for this beta section. Okay. It's going to be easy. This one is just a bit from the previous study by adding this member. Okay, adding this member. If we consider the whole structure, if you consider the whole structure, both this one and this member, you will see C is going to be hit, A is going to be hit. So if you connect all of this to be one piece, you have 1, 2, 3, 4. You cannot solve it. Okay. And then if you say, again, I will separate this member B from this member, and I got the free body that yes, you made a free body that. And then following this procedure, this is in, you have 1, 2. This is in, you have 1, 2. Then following this one, you got to have this one opposite direction, opposite direction, opposite direction, opposite direction. You have the total of what? This 4 and then 6. You have 6 unknown. And then you have what? You have equal to 3 body, then have half B. If you're going to have total equal to 6 equation, you have determine the reaction. But this is good enough for you. You study any static and techniques of magnet already. Is this good? You may have one more choice. Okay. Using the concept of a static or two-force member. Two-force member is what? Two-force member is the member that in on one and two end, and along its length, no force. It's going to be hidden, and then no force along the length. This is what? The same as the task member. This is going to be the same as the task member. If this is the same as task member, this member will have the force along its direction. Then, following that one, the free body can come to this one. And now, everything is supposed to be easier. You can determine the force on the reaction on this beam easily, right? And then I should note that after you get this one, this is going to be 106.7 and then cosine 45 degrees. And then this is 106.7 and then this is going to be sine 45 degrees. Since this is going to be 106.7, it's going to be F sub BC Newton. Okay. And then following this one, again, you may have this force X upon this one. Okay. And then you also have this force X upon this point, this support also. Now, you may cut it over here. After you cut it again, you can be involved of the internal process at moving. You have to by yourself because you have studied of this in engineering subtechnics. Okay, now let me move to more important things. There are a lot of determinate. You can see the gap between this to this to be, okay. And this gap indicates that each segment of the beam is going to be statically determinate. And in the construction again, the construction is cross beam. This is the cross beam, okay. And then before the construction the cross beam, they also construction the column, okay, and for sure, under the column, they are supposed to have foundation under the water, okay, and then for sure, most of that we got to put the pipe, okay. The order to form the pipe, the foundation, the pier, the cross beam, and then you are simple beam. Let me move to the shear and bending moment diagram. Let's call it in short SFD for shear force diagram, BMD for the bending moment diagram. And then we follow the procedure as before. This one subject can do the triangular, this beautiful. Okay. And then you have need the reaction for one. Okay. Then we should cut it for a given point. And then let's put it over here. Let's cut it. Okay. After you get the reaction, you may cut the segment of this one as the length of x, okay, from the left to the right. Then the left side over here still triangle. The triangle is going to be continuous loop, okay, triangle. This loop is going to be continuous. You can determine W over here easy by using similar triangle W divided by x. W divided x equal to 6 and then divided by, and remember the length for it obviously is 9 meters. So W is going to be 6 over 9x. Okay, or you may say this is going to be 2x over 3. Okay, so the triangular, this triangular, this triangular is going to be is the triangle is going to be linear. Okay, I just said linear equation. Okay. But for uniform distributed load, such as we have it, W is 10 kilonewton per meter. We call this load going to be constant. Okay, this is a constant load. And then any kind of loading, constant or triangular, is dependent on your construction. If you construction the wall as one, it's going to be uniformly this commutable. If you put it in triangular, the load going to be triangular distributable. If you put like you put correctly, triangular distributable. The load can be curved, okay, can be anything. But the concept going to be the same. After you get the reaction, you got to put sign convention for this m sub x. And then for this one, gonna be the shear v sub x. Okay. And for sure, v sub x is going to be this function. Hey, note on that linear function. This is going to be in the form of polynomial and then x squared function. Okay, it's going to be quadratic. What they call it? Quadratic polynomial function. Okay, and then cut the graph. If this is 0, is 9. If this is 9, it's going to be 9 squared over 3. 9 squared over 3 going to be 27. 9 minus 27 is going to be minus 18. Okay. Due to the quadratic function, this one going to be in the form of curve. And then that is 1 point over here, having the value of shear of 0. Okay. The shear of 0. This is important. You got to determine it. Okay, at this point, shear equal to 0, you can determine x by what? 0 equal to 9 minus x squared over 3. So x squared over 3 equal to 9. You solve it. Okay, x is gonna be 5.2. This is important because this one will provide the point of maximum moment. Okay. Why? Because df by dx equal to 0. The slope of the moving diagram is 0. When the slope is 0, you think about go and at the top, go down. And when it reaches the top, the slope of the bottom is 0. And now you may cut the moment diagram. And that should note that the moment function is going to be cubic polynomial equation. This is x cubed. Okay. This is x squared. This is x. It's going to be in order. And then at the end of this one, we got maximum moment of 31.2. Okay. Following what I've done in this pattern, there are some important things that I should mention again. Okay. The distributed force related to the shear force. Okay. And the shear force related to the moment diagram. First, we have dv by dx equal to minus w. Going back for the one, what I mentioned over here, w is 0. Okay. So slope over here is going to be 0. Okay. The middle of this one, at the middle of this one, about 4.5 meters. About 4.5 meters. I can know that at 4.5 meters, that is the W equal to 3. Okay. At that point, this one is supposed to be 3. That's going to be slope over here. S is going to be equal to minus 3 because this is minus W. Okay. And at the end of this one, W is 6. So slope over here, is going to be equal to minus 6. Now we have dm by dx equal to b. Okay. V over here is 9. So the slope over here, S is going to be 9. Over here, here is what? Here is 0. Slope over here is going to be 0. Over here is minus 19. Then the slope over here will be S equal to minus 80. And it should say for the slope positive is up. For slope 0 is over here. For slope negative downhill. Okay, you count the step. Slope is positive. Okay, and then you put slope is negative. That's going to be the sense of engineering. Okay, we transform mathematics into physical. Okay, get that right? Now, we have to our procedure that you already know about it. Okay, that's what we did. This is for the method of judge. We got to what? To write the shear force equation and the shear force diagram. And then we write the equation again and now we know bending moment diagram. And now I can to say something. W here is 0. Here is going to be constant. Moment is going to be linear equation. Okay. Right? Now, let us take to back with this example over here, and then the shear force diagram of this simple grip for many times, and you guys know very well about the shear force diagram and the link diagram of this one. Now, W is constant, And then shear is going to be linear equation. And this one is going to be what the equation is going to be x squared. Function of x squared is going to be function of x. This is going to be a constant. Now, in conclusion for the problem, okay, when you got to the shear force that at the order of equation mu, so that one will be up. When you got the moment that is going to be this is the first one is going to be certain up 1 degree. And then you got the negative moment that is going to be set up 1 more degree. This is going to be curved with more than this one. Yeah. More curved. Now we move to this one and shoot around like to stability. We use the whole empiric subtracting. Okay, and by following all of this example in PowerPoint, and also there are more. Okay, now following this one, we have some conclusion in view. Okay, and then for the shear, we have first dv by dx equal to minus w. You need to write it. Okay, that's how you recall you. And then second, you have delta v equal to minus of what? Area of w. We do it a u v. Okay, and then for the three, upward force delta v positive, downward force delta v negative. Okay, coming to this one, this is the reaction. Okay, this is upward force, upward. This is going to be upward force. The shear going to be plus 2.5. And then W here is 2. Okay, then you will have the slope along this one going to be negatively 2. So all of this is going to be slope in the negative s equal to minus 2. Okay. Then after that, along this leg, W is going to be 0. But before you go along this leg, what happened over here is going to be the value of V sub B. Following this one, V sub B minus over here 2.5, and it's going to be equal to negative of the area along this one is going to be minus 2.5. V sub B going to be minus 10 plus 2.5. This is going to be minus 7.5 as shown here. Okay. And then coming to this one, we have W is 0. So S over here is 0. This is going to be always taking the value of minus 7.5. Reaching over here, we have what? We have this C sub y. This C sub y would be up. Taking this one up. Okay. So first we have at the acting point of the upward. This one of the upward loading. The value of shear lag is increased by the reaction. The same over here. Okay. From minus 7.5, this one upward up over here. That's the meaning of it equal to the magnitude of the earthquake. Then that is the second thing. Coming to the moment that I can have what? First, df by dx equal to v. Okay. Second, I can have delta then equal to positive of area of the diagram. between A up to B. Then the third one, if you have clockwise movement, delta is positive. If you have counterclockwise, then delta is negative. Okay. And then to mention one more thing. If you don't have hit, okay, and then this one lower. If there is no external movement cannot be zero. Okay, cannot be zero. Then the slope of this one gonna be the shear. You may say following this one, S over here is gonna be 2.5. Okay. And then if you project this one, this is here equal to 0. If you project it to this point, that is a small point over here that has slope equal to 0. And what would be this distance? What would be this distance? 2.5 divided by 8. 2.5 divided by 8 equal to 2. So x equal to 2.5 divided by 2 is going to be 1.25. Then following this one, what will be the value of m over here? M over here minus m over here is 0 equal to the area here equal to 1.25, and this is 2.5. If you put this one into the calculator, it's going to be 1.25 times 1.25. You get the answer to be this one. And that's how you follow this note. Okay? This note. And then coming back over here, this is minus 12.5. This is going to be 37.5. What will be the mode from the negative to positive? This is due to this moment. This moment loaded in this clockwise direction. Then the moment change from negative 12.5 to 37.5 noted on this one. Okay, and then there are the other things, okay, to be noted as Ajahn did mention. This one going to be this one, and also this one going to be this one by putting the knowledge from method of section transforming to be the relationship between what? Between W, Shear, and M. Okay, and whenever this is 0, the W is 0, this one will be constant, and M gonna be linear. This is 0, this is constant, and this is linear. And then if this is going to be value, therefore you may put it to be constant value. This is constant value. Here going to be in this form like this one. Here going to be linear. And M is going to be like this one. M is going to be function of x squared or quadratic function. And I would like you to recognize this one. Since it's going to help you a lot when you know the shear force diagram and bending moment diagram based on that moment. Okay. Then you may come to this one again. The triangle and go to all of this detail that you study for ending static. And finally, you will get the equation. And then following the equation, you get this important relationship. And then one more thing, at the point of zero here, slope over here is going to be zero. At this point, we're going to have the maximum bending moment. And all of these one go to the example, and then we use those type of notions to develop the graphical method and follow the graphical method. Actually, the basic topic comes from this relationship. If you guys prefer to know about theoretical background, as you said, the theoretical background of this relationship, I asking you to go to the textbook of Professor Bipler to find the relationship among them. Okay, this group, shear force, and bending moment. For this derivation, you may go to all of that and you get the same conclusion that Adan has shown you. First, dV by dx equal to minus W. Slope of the shear diagram is the negative of the magnitude of the load W at that point. Second, slope of the movement diagram at a point is going to be positive of the transfer shear force diagram at that point. Third, we use the first one, expected as before. The change of the shear force between 2 points is going to be the negative of the area under load W between those 2 points. And then the fifth comes to the change of the bending moment between 2 points equal to the area under the shear diagram between those 2 points. And then the fifth, when the force, I just said, when the force up, they also be positive. When the force down, they also be negative. Okay, and then the last one, we have counterclockwise movement, and then clockwise movement, they also be positive. And then if you have counterclockwise movement, they also be negative. And that's all the conclusion we going to use to do the shear force diagram, bending moment diagram of the beam. And I want you to do, okay? I take 1 hour to explain the way you should and the point you should remember and understand it. Okay. Typically, for Professor Bipler textbook, you will get that one. And then coming to this one again, W0, okay, B is going to be constant, M is going to be linear. Then for this one, W is constant 50. Okay, we going to be linear, M going to be quadratic. Then for the triangle, W is going to be linear, shear quadratic, M is going to be cubic. Okay, there are a number of examples again in my PowerPoint, and I ask you to go through all of them. We have it for your midterm examination, and you will see the example in the PowerPoint is easier than extra example that I provide you. So, on this one will be close to, okay, this one will be close to her. You study statically, because it's all material already. You know, there was that and big moments that are 2 times a week. This will be the 3rd time, and next will be the 4th time. The next one. Then, let's go to all of this by yourself. I have 2 more examples to show you guys. And then later, next time, that will come with the normal force, shear force, and bending moment diagram of the wave. By the time, any question? If no question, then we take 5 minutes and we will come back to work together on the example. Let us take a look at this extra example. It's going to be one of our 2 extra example. We have the beam, okay? And if you consider this beam, it said it has the support fixed at A and lower at C, and also have the internal hinge at point B. If you consider the whole beam together, you will have the reaction 1, 2, 3, and then 4. So free body of the beam, the beam A, B, C has 4 unknown reaction. But happen is the same as we know, since there is 4 unknown, you cannot use the equation of equilibrium to solve it. So therefore we must the free body diagram of A, B and BC to determine the reaction. That's going to be our first analysis step to show you understanding for this kind of problem. Now, to dock it, you may follow what you have learned previously. Just make a copy of this one. The first one over here for A, B. And then you may spacing it for 1.5 centimeter and then measure this one 2.6. So you draw another portion of the beam. Then drawing the free body diagram require you to specify the reference X and Y axis. You may write it anywhere. And then this is going to be A, and then B, and C. Under application of the force of this one, you should have the reaction occur over here A sub Y. This one gonna be A sub X, and this one gonna be M sub A. And then also for the second portion, this one subjected to uniformly distributed load and also external moment 800 kilonewton meter. And subjected this one, we have the reaction occur at the roller to be C sub Y. Now we have internal hinge at this point B. Then which one going to be the starting point for me? This one is less complicated or complex compared to the AB. So if I consider this one, Ajahn may assume and believe the reaction over here B sub Y should be upward. Since B sub Y upward, this one should be B sub Y downward. And then for the horizontal force, this one point in. This one gonna be in the third law of Newton, gonna be B sub X. Now we have total of 6 unknown. And then we have with 3 times 2 free body diagram equal to 6 equation. Which portion you should start first? If you consider this portion, this free body diagram has total of 5 unknown. We cannot start at this portion, it's better to consider this portion. Free body diagram of this one has only three unknowns. So from consider the free body diagram of the segment BC. We start with that one, segment BC. And then if we consider BC, you may zoom it and you may starting using equation of equilibrium. And one of the best equation of equilibrium, even though you have summation f sub x equal to 0, f sub y equal to 0, we usually use this moment equation because it can eliminate the unknown. So we take summation of the moment m sub b equal to 0, eliminate b sub x and b sub y, determine c sub y counterclockwise rotation gonna be positive. C sub y. You got to put the length to show the moment arm over here. That's gonna be 6 meters. So your free body diagram gonna be more complete. Then you also have 800 in the opposite direction, and also resultant force of this one is 150 times 6 rotate in opposite direction equal to 150 times 6, and moment arm over here gonna be 3 meters, and then this one gonna rotate the same direction of this one plus 800. You put it, you should get c sub y equal to 3,500 divided by 6, and that's gonna be 583.33 kilonewton. And please help me specify it. Your results over here. Okay, you have this one equal to 583.33 kilonewton. Then, if you have summation of f sub x equal to 0, now your b sub x gonna be 0. This is 0. And the last one, move it up. We have summation of f sub y equal to 0. B sub y upward, put positive upward. And then this one, 583.33 plus 583.33 upward. And then we have resultant force, this one downward, minus 150 times 6. Okay, this is gonna be 900 actually. So our b sub y gonna be 900 minus 583.33. You should get this one 316.67 kilonewton. And equation, we determine the reaction of this one equal to the same 316.67 kilonewton. Okay. So you move to the next free body diagram. Okay. We now have B sub x and B sub y. Our free body diagram now have reduced the number of unknown from 5 to only 3. Okay, we know this, only 3. This is 8 meter, this is 4 meter. Which equation you prefer to use first? It's up to you. Okay, you may think like consider the free body diagram of the segment AB. Okay, now we may have the summation of the moment above A, over here to be 0. Eliminate a sub x and a sub y, and rotation of this one to be positive. So m sub a rotate in this direction 700 kilonewton opposite b sub y opposite equal to 700. Moment arm gonna be 8. This one rotate clockwise opposite 316.67 times 12 meter. Okay, putting all of this together, we will have m sub a equal to 9,400.04 kilonewton meter. Put it over here. 9,400.04 kilonewton meter. And don't forget, put the direction too, because moment and force, they are vector. Okay, b sub y over here 316.67 kilonewton, and this one upward magnitude and direction c sub y 583.33 kilonewton, and then upward. Okay, and then if you prefer summation of f sub x equal to 0, this a sub x gonna be 0. This is 0. This is 9,400.04 kilonewton meter. Okay, put it over here. Now we have one more left for summation of f sub y equal to 0. This one upward to be positive, a sub y upward. This one downward equal to 700. This one downward 316.67. A sub y gonna be 1,016.67 kilonewton. Double line. Okay, so we have a sub y 1016.67 kilonewton, and then it's upward. That's going to be the first portion. Okay, based on this one, you got the total of 2 and 4. Oh, 6 points. Okay, maybe put all there. Then come to the shear force diagram that we have. We got to put this one to be x meter, and then when we run from the left to the right, 0, and then 8, and then 12, 6 more, 18. Okay, 18. Then you got to put a proper scale. Okay, you may use 1,000 kilonewton, and then per 10 millimeter. Sure, that's going to be maximum force, going to be 1,000. This is going to be a sub y. Okay, that's going to be 1016.67 kilonewton. Larger than this one. That's going to be only 1 centimeter if you prefer. Okay, and then you should put this axis to be V in kilonewton. Coming over here, first, dV by dx equal to minus W. We won't use it. Second, we have delta V equal to minus area of W between A to B. We won't use it, but we're going to use the third. We have upward force, and our delta V is going to be positive. Start with this one, and with this value 1,016.67 kilonewton. You don't need to put kilonewton because the kilonewton is already here. Then W here is 0. Let I show you. When you draw shear force diagram, you see the problem. So slope is gonna be 0. dv by dx equal to 0. Since the slope is 0, this is going to be 1016.67, the same as before. Then 700 down, that's going to be about 7 millimeter, putting in downward. Okay, then the value over here going to be 1016.67, and then gonna minus 700, and then you should get this one to be equal to 316.67, and that's gonna be slope over here. Slope over here gonna be 0, putting over here, and dv by dx equal to 0, and you may put the arrow to indicate your value like this one. Now, coming up to this point you have 16 downward, so this is downward. You move to this one upward, this one take the upward. So go back to 316.67 as before. Now, W is 150 kilonewton per meter. So now dv by dx in this B to C is going to be minus 150. Then it's going to be minus like downward like this one. What's going to be the value here? We come to this one. We sub C. This is point C. Minus. This is point B. This is point B. This is point B. Minus. It's going to be minus 316.67. And then it's going to be minus equal to minus the area of this one. Minus of 150 times 6. So our V sub C gonna be minus 900 plus 316.16 is gonna be 583.33 kilonewton. You down here, and that's going to be this value about 5.8, and this is going to be your V sub C. It's better to indicate it minus 583.33, and then you're going to get this like a curve. Then you have upward force of this one process. Okay, you got to have this one, and then this one 0, this one important x for the slope over here 316.16 divided by x is going to be 150 slope. Then x over here you can determine it to be 2.111 meter, and if you like to determine the other side over here, it's going to be 6 minus 2.111 is going to be 3.889 meter. Okay, and that's going to be your shear force diagram. Dot it. Take a look at the problem. Okay, now we are ready to draw the bending moment diagram. Do the same thing. Okay, we got to take x over here meter, and then this is 0, 8, 12, and then 16. Put this in the m in kilonewton meter. Okay, and then we have first dm by dx equal to v. Second, delta m equal to minus of area of v diagram between
A to B, and then third, counterclockwise moment delta M. This is clockwise. Delta M positive, and then counterclockwise moment M, delta M negative. We come to this point, and then we have what? We have M sub A. Guys, take a look at this one. M sub A is what? M sub A is what? M sub A rotate counterclockwise. So M sub A start with negative. Okay, 9,000. So scale. You got to call scale. Okay. You cannot put 1,000 kilonewton meter per 10 millimeter because we don't have 9 centimeter over here. We don't have. We have only 8 centimeter. So the scale should be only 2,000 kilonewton meter per 10 millimeter. So this is 2,000, 4,000, 6,000, 8,000. This is gonna be 10,000, and then we have 9,400. This is 9,000. This is supposed to be the point of minus 9,400.04. Okay, this is going to be negative. Then the shear always positive. So we should have dm by dx over here equal to 1016.67. Okay, and then when we arrive here, what's going to be the moment here? Coming into this one, m over here, minus m over here, minus of the minus 9,400.04. And then it's going to be equal to, this is wrong. This is going to be positive. Okay, it's not negative. Negative gonna be this one. Okay, this is gonna be positive. So this is gonna be equal to the area there, 1016.67 times 8. So m gonna be equal to 1016.67 times 8, and then negative change to be positive, and then move to this one, minus 9,400.04. Okay, you're gonna get this one to be minus 1,266.67 kilo Newton meter. Okay, underscore it. And then following what Ajahn show you here, that's gonna be 1,000 something, about 6 millimeter. That's gonna be about this point, and then draw the line, linking between these 2 points, 9,000 and this one, 1,266.67. Okay, and then you may note on the slope. Then slope change, because the shear change dm by dx equal to the shear 316.67. And Ajahn should note that, very important, guys. This is internal hinge. What's going to be internal hinge? M sub b gonna be 0, right? So you don't need to think much. This one gonna be 0, and then you have this one and indicate your slope. You can check. Okay, you can check by using the same one over here. M sub b minus 1. This is minus 1,266.67 equal to the area here. You can check. Okay, if you like, you can check. That's going to be equal to 316.67 times the length here of 4. Okay, M sub B gonna be 0 for sure. Then coming into this one, slope still be the same, 316, but there is the slope over here. That's gonna be dm by dx equal to 0. And the moment here is what? M over here minus 0 over here is gonna be equal to what? Equal to the area here. Okay, equal to 1/2 of 2.111 and then time 316.67 the area here. Okay, you will have M equal to 334.25 kilonewton meter. That's going to be very small. Okay, very small because 2000 is 10 millimeter. That's going to be very small, 1.5 millimeter, something like this one. So 4.25 and slope gonna be 0. This is gonna be curve. Okay, this is gonna be curve. Then what's gonna be the moment over here? Okay, come over here. M sub C minus 334.25 and then you got to compute for the area here. Okay, that's gonna be equal to 1/2 3.889 and this is minus 583.33. M sub C gonna be minus 800 kilonewton meter. Okay, that's about 4 millimeter. That's gonna be minus 800 and then you got to have the slope over here. Okay, slope over here. Slope over here what? This is gonna be dm by dx equal to v minus 583.33. Okay, that's gonna be your moment diagram. And then what? At the end of this is what? Clockwise. Okay, when it's clockwise, it's gonna be positive. So it's take this one up and close this over here. Okay, your beam gonna be negative curve here, negative curve here, and this positive upward here. Okay, and that is going to be the first example. I got to determine the reaction for the next one. Let me move. Okay, you may try this one later. Coming the next one to match with the Thai segment. This beam have one portion, have second portion, and then have the third portion. This beam gonna have 3 portions more than the previous one. Okay, and then if we determine the reaction, this is pin 1, 2, and 3, and 4, and then 5. For the free body diagram, we have 5 unknowns. Okay, that's gonna be larger than 3 times 1 free body diagram equal to 3 equilibrium. Okay, so that we separate. Okay, we separate the beam. We separate the beam into 3 segments. Okay, and then we draw the free body diagram object. Let's start with the first one over here. Let's take the pink one. This is going to be the first one, and then you should space it for a bit. And this is 2.2. This is about second one, and mark it over here for the loading. and then this is gonna be 2.6. Make it the third portion over here. Separate them. So we have this first one, second one, and then we have the third one. Okay, let me stop this one a bit in order to have time to convert it. Okay, next we have three portions, and then you can put the reaction the same as before. This is gonna be A sub Y. This is gonna be your A sub X. This is gonna be your B sub Y, and the load gonna apply on the top kit. Okay, the top kit, and then we have this second one. This is 120 kilonewton, no reaction yet, and this is going to be 10 kilonewton meter. This is 10 kilonewton per meter, 15 kilonewton per meter, and then over here we have reaction of this one G sub Y, and this one for F sub Y, and this is 8 meter, 5 meter. Okay, and then for this one, you also have 5 meter, 8 meter. Now, you can see we have two hinge. Then at the hinge, we supposed to have the reaction also. Let me put this one at the point E to be E sub Y. And then this is gonna be E sub Y. And then put this one because I can consider the orange element. Subject only 120. So this one should have E sub Y and also C sub Y. Since we know this one upward, so when this one downward, this one upward, this one C sub Y should be downward. Okay, and then we have the length of this one. Which one you going to start first? Which one going to be our first free body diagram? You got to consider 4, 1, 2, 3, 4, and then 5, and then this is 5, 6. This is not good. Okay, and then this is going to be E sub X. This one 1, 2, 3, 4. Or have 1, 2, 3, 4. But you can see this has 3 vertical. This has 3 vertical. Only CE has 2 vertical forces. So we will start with the free body diagram. Consider free body diagram of CB, and then you may mention due to the symmetry, you may say E sub Y equal to C sub Y equal to 120 divided by 2. That's gonna be equal to 60 kilonewton, and this is equal to 60 kilonewton. Okay, and then we consider free body diagram. For sure, we should start with this one, the green one of EFG. Okay, on EFG, if you do summation of x equal to 0, you will have E sub x equal to 0. Now, you have only 2 more. You may take the moment summation of the moment about G equal to 0. Take G. So, F sub Y rotate in this positive direction, time 8, upward time 8. And then we have this one opposite equal to 60 times 5.8, and then you also have this one, the area gonna be 10, this is 13, that's gonna be plus 130. Length from here to here is gonna be 13 divided by 2 times 13 divided by 2. F sub y should be 203.13 kilonewton. Okay, that's gonna be your F sub y, 213.13 kilonewton. Then summation of F sub y equal to 0 upward to be positive, G sub y upward, plus this one, 213.13 upward, and then opposite, this one, 130, right? 130 is correct, yeah. And then plus this one is gonna be 60. So you should get G sub y. Okay, 180 minus G sub y. 180, that's it. Oh, that's going to be negative 180, negative 13.13 kilonewton. Or G sub y going to be 13.13 kilonewton downward. So this direction is not correct. It's going to be in this direction, 13.13 kilonewton. Then we just move to this one. Summation F sub x equal to 0. Now, C sub x is 0. And then summation F sub x equal to 0. A sub y also 0. We have the last one. Consider the free body diagram of A, B, C. Okay. And then you may take summation of the moment about A. Take over here to be 0. B sub y gonna rotate in this direction to be positive. B sub y times 8 rotate this way. The order, this one won't equal to 15 times 13. And then from here to here gonna be 13 divided by 2. 13 divided by 2. Okay, and then 60 plus. Okay, 60 gonna rotate the same way as this one. This is 15 times 30. Okay, and then 60 gonna time total of 13. So B sub y should be 255.94 kilonewton. That's gonna be this one, 255.94 kilonewton. Then summation of F sub y equal to 0. You have A sub y plus 255.94 B sub y equal to this one, 60. This one downward, 15 times 13. You got A sub y. Now you got A sub y to be only 0.94 kilonewton. A sub y very small, and then it's also negative. Okay, so A sub y gonna be 0.94 kilonewton downward. So revert this one to be downward and 0.94 kilonewton. Okay, that's going to be the lecture number 6. Okay, if you have any question, you may ask me later. Okay, there are people waiting for us. I should finish the lecture here. Okay.